Great. Yeah. So thank you so much for having me. It's very cool to be here. And yeah, I'm Alexandra, and I'm a grad student at MIT. And I'm going to talk to you today about building homomorphic encryption from new assumptions. And this is joint work with Henry, Yal, and Vinod, and it appeared at Eurocrypt a couple weeks ago. Okay. So I probably don't need to introduce this for this audience, but an encryption scheme is homomorphic if it lets us compute directly on without ever decrypting the data first. So to be a little bit more specific, in this setting, we have a user that can sample a secret key and an evaluation key. And now our user can publish its evaluation key and can publish encryptions of any messages of its choice under its secret key. So here, for example, our user is publishing encryptions of the messages x1 through xm under its secret key. And now any other party, so for example, this server here, who has just received these ciphertexts and received this evaluation key, can evaluate functions directly on this encrypted data. So here, for example, our server can take this function f that's in the supported class of computations and can produce the ciphertext that encrypts f applied to x1 through xm, again, without ever decrypting and without ever learning anything about x1 through xm. So to be a little bit more formal, we say an encryption scheme is homomorphic if it meets three properties. So first of all, our encryption scheme needs to be secure. First of all, let's say it needs to be correct. So this really just means that the ciphertext produced by the server here really does decrypt to the function evaluation f applied to x1 through xm with good probability. So say for this talk, probability something like 2/3 is enough, and then you can always amplify this by repeating the scheme many times. Second of all, we need our scheme to be secure. So this here really means that the server should learn nothing about the user's encrypted data. So more formally, the ciphertext and the evaluation key together reveal nothing about x1 through xm. And finally, our scheme needs to be compact, which means that the bit length of each of the ciphertexts here should not grow with the complexity of the function f that's evaluated on them. And the reason for this requirement here really is because you can think of what I've shown you here as a protocol for outsourcing the evaluation of f to the server. So really, we just want to rule out trivial constructions where the server basically just sends f to the user. But we want to be able to do better than that. Okay, so this is homomorphic encryption. And I want to point out that really the evaluation key and the secret key just need to be sampled once, and the evaluation key just needs to be published once. And after this, our user can sort of encrypt as many messages as it would like, and our server can really evaluate as many functions as it would like. Okay, and the reason why we care about homomorphic encryption is because a long and very fruitful line of work has shown that if we can build homomorphic encryption, then we get a whole array of privacy-preserving applications. So for example, you could imagine that the function f that's evaluated by the server here is some machine learning model or some genome analysis or web search functionality. And so with homomorphic encryption, we can retain this functionality. So we can have our server evaluate this function without ever learning anything about the user's inputs. And so really, this gives us a very strong form of user privacy. Okay, so as the definition that I gave you implied, homomorphic encryption is really a primitive that exists along a spectrum depending on the complexity of the functions f that can be applied to ciphertexts. So at the bottom here, least powerful, I have private key encryption, which is not homomorphic. So it can't perform any computations on ciphertexts. Then sort of above this, we have linearly homomorphic encryption, which can evaluate linear functions on ciphertexts. So this means it can just perform any number of addition gates. And at the top, most powerful, we have fully homomorphic encryption, which can evaluate any function on encrypted data. So really, for the purposes of this talk, you should think of this as evaluating any number of addition and multiplication gates on ciphertexts. And so in between linearly and fully homomorphic encryption here, there's a huge range, which we generally refer to as somewhat homomorphic schemes. And these schemes become more and more powerful as they're able to evaluate more and more multiplication gates. Okay, so what do we have today? Well, the encryption schemes that we use every day on the internet, like AES, which are one-way functions, don't have any homomorphism. But we can do better. And so specifically, a whole suite of number theoretic crypto assumptions from the 1980s give us linearly homomorphic encryption. And in fact, they also give us a little more, because a very cool line of work has shown that they can evaluate certain nonlinear functions, and specifically certain branching programs of small length on encrypted data. Then in 2005, we learned that using cryptographic pairings, you can evaluate degree 2 polynomials. So this is one multiplication gate followed by many addition gates on encrypted data. And then in 2009, in a huge breakthrough in cryptography, we learned that using lattices, you can get all the way to fully homomorphic encryption. And more recently, also that we can get there via the machinery of indistinguishability obfuscation. But really, in terms of what we know and how ways to build homomorphic encryption, today, this is it. So this is the entire landscape. We only have this handful of approaches. And specifically, if we want to build homomorphic encryption that can support additions and multiplication gates, so these polynomials of degree 2 or more, really the only approaches that we have are using lattices or using pairings, which come up in pairing crypto and also in all indistinguishability obfuscation schemes that we have. So this talk today is going to be about introducing a new way of building homomorphic encryption. And specifically, we're going to be building a scheme that's somewhat homomorphic. So we're going to be in this middle range here, where we're going to be able to compute a few multiplications followed by many additions on encrypted data. And to build this new scheme, we're really going to combine two tools. So first, we're going to take a linearly homomorphic encryption scheme. So this is this balloon here given to us by number theoretic crypto. And we're going to show how to lift this linearly homomorphic scheme into a somewhat homomorphic one by adding in just one additional assumption. And this is an assumption that on its own has no homomorphism. So on its own, it just gives us private key cryptography. But what we're going to see is that when we put these two things together, we get something that's much more powerful than either individual part. Okay, and so you might wonder, why should we care about this? We already have fully homomorphic encryption. Why does, a new construction of somewhat homomorphic encryption matter? And really, I think there are a couple of reasons why this is different. The first being this is from new assumptions. So again, this is the first homomorphic encryption for polynomials of degree 2 or more that doesn't use lattices or pairings. The second is, we'll see it's a relatively simple construction, so we'll try to walk through the entire construction in this talk. And finally, I think it really gives us sort of a new point in the design space, and there are tons of open questions, and I think there are many exciting directions to take this further. Okay, so that's what this talk is going to be about. So we're going to see how to combine this sparse learning parity with noise, or sparse LPN assumption, which is this assumption that on its own just gives us private key encryption. And we're going to put this together with a linearly homomorphic encryption scheme to build somewhat homomorphic encryption. And to be a little more specific, this somewhat homomorphic scheme is going to be such that for any parameter n that's polynomial in our security parameter, and that we choose at encryption time when we're building our ciphertexts, then any party that wants to evaluate on these ciphertexts is going to be able to perform just slightly less than log n multiplications followed by n additions on these ciphertexts. And I should say these operations, so these additions and multiplications are going to be over fq, where q is some prime that you can think of as just 3. Okay, and so let's begin by diving into it, what exactly this sparse learning parity with noise assumption is. So this assumption was introduced in cryptography by Alexandra in 2003, and it's based on the following problem. So say I sample a random matrix A, which is sparse. So to be a bit more specific, A is going to have entries that are values mod q, and it's going to have dimensions m by n. And when I say A is sparse, I'm going to mean that each row of A is going to have exactly k non-zero entries, where k is some sparsity parameter that you should just think of as super constant. Okay, so we have this sparse matrix A. And then I'm also going to sample a much shorter secret vector S. So S here is truly random of dimension n. And I'm going to publish A and publish A times S, corrupted with some random noise. And specifically, I'm going to sample this noise here so that most of its entries are 0, but with some really small inverse polynomial probability. So n to the minus delta for any constant delta that's between 0 and 1. So if you want, just think of delta as like 0.1 or 0.5 or something. So with very good probability, every entry in E is 0, and with very small probability, n to the minus delta, these entries are going to be truly random. So they're going to completely corrupt the value at that position. Okay, so I'll publish A, and I'll publish A times S plus this noise term E. And I'm going to ask you, can you distinguish this from a random sparse matrix A and a truly random vector B? And it turns out this is actually a computationally hard problem. So to the best of our knowledge, there are no efficient algorithms for this task. And this is actually closely related to the hardness of solving random constraint satisfaction problems and other problems in average case complexity. And so this is good news for us because we're going to use this problem here to build cryptography. And so just to give you a little bit more context for this sparse LPN assumption. So this assumption, the problem becomes harder, so the assumption becomes weaker the more noise you add. So in higher noise settings, we have reductions that show that the standard LPN problem implies the hardness of this sparse LPN problem. But in this noise setting, which I've given you here, so with this inverse polynomial noise probability, what we know is just that sparse LPN gives us a handful of cryptographic primitives that are very cool. So it gives us things like constant overhead pseudorandom generators and multi-party computation, a few pseudorandom correlation generators, and a very cool construction of homomorphic secret sharing that inspired this work. Okay, so this is this sparse learning parities with noise assumption. And now what I wanted to do is I just wanted to give you one quick fact about sparse LPN that was proven in this work on homomorphic secret sharing by Dao, Shai, Jane, and Lin. And what they showed is that not only the sparse LPN, is it true that it looks computationally indistinguishable from random if you publish A times S plus E, but you can also use this to sort of hide linear functions of the secret. So what I mean by this is that for any sort of scalar x, you can publish A and then A times S plus E plus X times your secret, and still for an appropriate distribution over A matrices, this is going to look like a random sparse A and a truly random vector B. So really, the only takeaway I need you to have here is that you can also hide these linear functions of the secret. And really, the technical term for this is key-dependent message security for linear functions. Okay, so that was it. That was all we're going to need about sparse LPN. And now we're going to use this assumption to build a homomorphic encryption scheme. And to build this homomorphic encryption scheme, we're really going to proceed in 2 steps. So first, in a first step, we're going to use this sparse LPN assumption to homomorphically add and homomorphically multiply. So this might seem weird to you, right? Because I told you that we can't get homomorphic encryption from sparse LPN on its own. So why aren't we already there? And the reason is that this scheme actually does not give us a full-fledged homomorphic encryption scheme because it has a major caveat, which is that its ciphertexts are going to be huge. So it's not going to be compact, and so it's really not on its own going to meet our definition of homomorphic encryption. But the good news is that this scheme does have one very appealing property, which is that decrypting these huge ciphertexts is very simple. And specifically, it's just going to require evaluating a linear function in the secret key. And so then, in a second step, what we're going to do is we're going to combine this with a linearly homomorphic encryption scheme to let us shrink down the size of these ciphertexts and get to somewhat homomorphic encryption. And so what I'll do now is I'll walk through each of these two steps in much more detail. And we'll begin with the first step. So the first step here is going to be to use sparse LPN to homomorphically add and homomorphically multiply. And this here is really heavily inspired by two prior works, and it can really be viewed in two ways. So one view of what we're doing here is we're taking this homomorphic secret sharing scheme by Dow, Ishai, Jane, and Lin, which lets you perform homomorphic computations on secret shares if you have at least two parties. And we're showing how to make this work with just one party. So running everything on just one server. And technically, the way this works is by sort of replacing the use of secret sharing with an encryption from sparse LPN. And the second view of what's going on here is that if you're familiar with the Gentry, Sahai, Waters fully homomorphic encryption scheme from lattices, we're really modifying the scheme to replace the use of LWE in lattice assumption, so with this sparse LPN assumption. And so really it turns out these two views of our scheme are equivalent, and they give the same scheme. And so you can find many more details on the first in our paper, and I'm really going to be focusing on the second view in this talk. And again, if neither of these two views made sense to you, that's totally fine, because I'm going to try and explain how we build this SHE scheme and how we use sparse LPN to add and multiply from the beginning and from the ground up. Okay, so how is this going to work? Well, at a high level, our scheme is going to look like the following. So what we're going to have is we're going to have our ciphertexts just be matrices. So when our user wants to send encrypted data to our server, it's just going to send a bunch of matrices to our server. And now our server is going to operate on these matrices and send a matrix which encrypts the result of the computation back to the user. And the way we're going to have these homomorphic computations work is that whenever our server wants to perform sort of an addition gate onto ciphertexts, all the server is going to have to do is to add the corresponding matrices. And whenever our server wants to perform a multiplication gate onto ciphertexts, all our server is going to have to do is to multiply the corresponding matrices. And finally, we're going to want to have one additional property on our scheme, which is that decrypting these ciphertexts should be linear. So whenever our user gets back this matrix that encrypts the final result of the computation, our user should just have to apply a linear function to this matrix to get out the encrypted value f of x. Okay, so this is what we want to achieve. And again, for those of you who are familiar, this should really sort of look like this Gentry, Sahai, Waters scheme, in that our ciphertexts are matrices, addition is matrix addition, multiplication is matrix multiplication. But here we're trying to port it to using this LPN-based encryption. Okay, and so how are we going to do this? Well, so following in the footsteps of Gentry, Sahai, and Waters, we're going to do this by having our ciphertext satisfy one key equation. So specifically in our scheme, we're going to sample our secret key to be a random vector s of dimension n, which should sort of remind you of the vector s in our sparse LPN assumption. And now to encrypt any value x, the way we're going to build a ciphertext is we're going to have our ciphertext be a sparse matrix C, into which we've embedded this value x as a noisy eigenvalue. So what exactly do I mean by this? Well, I mean that our ciphertexts are going to have to satisfy this blue equation, which says that if I take the ciphertext matrix C and I multiply by this vector minus S1, which you can think of as sort of the extended secret key vector, then what I should get back is the encrypted value x multiplied again by this extended secret key vector. So this here really means that x is an eigenvalue of C and the extended secret key vector is an eigenvector. But I'm going to allow for some sparse errors here. So I'm going to allow for this equation here to be corrupted in some locations as long as it holds in most of the locations. Okay, so what we're going to do is we're going to ciphertexts that satisfy this special structure. And so first you might ask, how can we do this? How can we embed sort of a noisy eigenvalue into our ciphertext matrix while still ensuring that our ciphertext hides this value x that we're trying to encrypt? And the way we're going to do this is exactly using the sparse LPN assumption. So specifically, our ciphertext here is going to be, consisting of two components. So first, we're going to sample sparse matrix A. And then we're going to append one more column to it, which we're going to compute as A times our secret key S, plus some sparse LPN errors E, plus our message X, times this extended secret key vector. So if you stare at this for a bit, you see that this ciphertext C that we built here indeed satisfies the blue equation. So specifically, if we were to multiply C by this extended secret key vector minus S1, what we would get is a minus A times S in the first term, and then a plus A times S plus the errors plus X times the extended secret key in the second term. So really, we get this nice cancellations of the A times S's, and we're left with exactly what we need. So we're left with exactly the errors plus X times the extended secret key. So that's good. So it satisfies this blue equation. And the other thing that we see is that because of the sparse LPN assumption, and specifically because of the key-dependent message security, so because it's secure even if we hide sort of linear functions of the secret key, the ciphertext here really computationally hides our encrypted value. So this is great, because this means that any observer who only sees the ciphertext and doesn't know the secret key cannot determine what X is. Okay, so I just argued that we can build ciphertexts of this special form, but I still haven't told you why this is useful. And really, the reason is because it's going to let us perform homomorphic operations really easily. Specifically, whenever we want to perform a homomorphic addition gate onto ciphertexts, we can just add the corresponding matrices, and this is going to give us an encryption of the sum of the underlying messages. And really, sort of abstractly, the reason why this works is because if you have two ciphertexts with the same eigenvector and you add them, then you get a ciphertext with the same eigenvector and the sum of the corresponding eigenvalues. So if we want to formally prove this, the way we would do it is we would look at the ciphertext that's output by this addition gate, so Cx plus Cy, and we can just think about multiplying this with this extended secret key vector. And when we do this, what we get out when we sort of rearrange things in group-like terms is that we see that this new ciphertext encrypts the sum of the underlying messages. So it now encrypts X plus Y, and its new error term is the sum of the prior two error terms. So it has something like only a 2 times higher error rate. And finally, our ciphertext is still sparse, so it's only something like 2 times less sparse. Okay, so that was the first step. So we've just argued that we can perform homomorphic additions just by adding these ciphertexts. And it turns out homomorphic multiplications work in exactly the same way. So specifically, we can perform a homomorphic multiplication gate just by multiplying two matrices. And what this is going to give us is an encryption of the product of the underlying messages. And really, intuitively, this is for the same reason. So if you have two matrices with the same eigenvector and you multiply them, you get a matrix with the same eigenvector, and the corresponding eigenvalue is now the product of the underlying eigenvalues. So again, here we can prove this by looking at the product of the matrices, so Cx times Cy, and thinking about multiplying this by the extended secret key vector. And then when we sort of expand this in group-like terms, what we see is that this indeed is a ciphertext that encrypts the product of the underlying messages. So it now encrypts X times Y. And the new error term here is going to be something like Y times the X error plus the X ciphertext times the Y error. And so crucially, because our prior two errors are sparse, so EX and EY here are sparse, and because the ciphertext matrices themselves are sparse, we can still bound the sparsity of this new error term. So what we know is that if our ciphertext matrices are something like k sparse, so they have k non-zero entries, then the error right here is only going to be something like k times higher. So still we can bound this error growth. And again, we can also bound the sparsity growth of these ciphertexts. Okay, so this is it. This was multiplication. And the last thing we said we wanted is that decryption is just a linear function. And indeed, because this blue equation here is satisfied, to decrypt a ciphertext, all we need to do is we need to multiply by this extended secret key vector. And then what this is going to give us back is the encrypted value x multiplied by the extended secret key vector plus some sparse error term. So what we can do is we can just look at the last entry of this output here, which is going to be x times 1. And with good probability, this is not going to have an error. And so this is just going to give us back the encrypted value x. So really, this is it. This is the entire construction. And so what we just built is we built a scheme from Sparse LPN that's correct, that's secure, and that's also homomorphic. And so I won't sort of bore you with the details of the error analysis here, but when you step through this, you see that if we have an initial secret dimension of n and an initial Sparse LPN error rate that's n to the minus delta, then what the scheme lets us perform is just slightly less than log n multiplications, followed by just slightly less than n to the delta additions. And after this, we'll still be able to decrypt correctly with good probability. So really here, this is great because n here is just a parameter of our scheme, right? So we can set n to be as big as we would like to support however many homomorphic operations we want to be able to perform. Unfortunately, though, what I just said is really bad because n here is also the dimension of our ciphertexts. So what I said is that if we want to compute more, we have to make our ciphertext bigger and bigger and bigger. And it turns out this gives us a scheme which is not at all compact. And specifically, the bit length of each of our ciphertexts, both sort of the ciphertext sent from the user to the server and the ciphertext sent from the server to the user, is bigger than the bit length of just the function f that the server can apply here. So really, our server would be much better off in terms of communication by just sending f to the user instead of operating on and then communicating these really huge ciphertext matrices. Okay, so this is bad, right? What we just said is that we can compute on these ciphertexts, but they're so big that we might as well just send around the function. And so really, it seems like we've done nothing useful here. But the good news is that we've only used one of our two ingredients. And so we're going to try and save this by adding in a linearly homomorphic encryption scheme. And so specifically, what we have right now is a way for our server to compute on these large Sparse LPN ciphertexts. So specifically, we have our user upload a large Sparse LPN ciphertext. So for example, this encryption of x here to the server. So this is just some sparse matrix. And then our server computes on this sparse matrix, performs additions and multiplications. It's going to get slightly less sparse. And then our server is going to hold this large encryption of the function f applied to x. And so now, really, what we would like is to give our server a way to shrink down this large output ciphertext, and specifically to translate it to encryption of the same value f of x under a compact encryption scheme. And specifically, what we're going to do here is we're going to give the server a way to translate our large, bulky Sparse LPN ciphertext into a ciphertext from a linearly homomorphic encryption scheme. And the way we're going to do this is by observing that based on the way that we constructed things, decrypting this Sparse LPN ciphertext is just a linear function. So really, there exists some linear function, which I'll call fdec here, which takes in the Sparse LPN secret key and produces the output of decryption, which is just the value f of x. And so now what we can do is, because decryption is just a function, we can evaluate this homomorphically. And so specifically, because it's a linear function in this case, we can evaluate it homomorphically under a linearly homomorphic encryption scheme. So what we're going to do is we're going to publish a linearly homomorphic encryption of our sparse LPN secret key. And what this is going to let our server do is it's going to let us homomorphically run this decryption function on our linearly homomorphic encryption of the secret key. And this is exactly going to produce a linearly homomorphic encryption of the output of decryption, which is just f of x. So really, it's going to give us a linearly homomorphic encryption of the same message f of x. But now we've translated from this large, bulky sparse LPN ciphertext to a compact linearly homomorphic scheme. Okay, so really the takeaway here is that we can translate from this scheme with the huge ciphertext to a linearly homomorphic scheme by just running decryption sort of under encryption. Okay, so now we're already much better off because our server doesn't have to send this huge sparse LPN ciphertext to the user. And instead, our server can just send this much smaller linearly homomorphic ciphertext to the user, which we know is compact. But you might still point out that we still have this problem of having these huge input ciphertexts. So the user here still has to upload a huge sparse LPN encryption of x to the server to even be able to compute in the first place. And so the good news here is that we can apply basically the same trick again to solve this problem also. So specifically, instead of having our user send up an encryption of x under this large, bulky sparse LPN scheme, we're instead going to have the user send up an encryption of x under a different compact encryption scheme, which I'll just denote as the orange scheme here. And really, all we need is that this orange scheme here has a cheap decryption function, which is cheap enough for us to homomorphically evaluate with our sparse LPN ciphertexts. Because if we can do that, then we can really play the same trick again. So we can have our user upload just the small sort of orange encryption of x, and we can have our user publish an encryption of the orange secret key under our bulky sparse LPN scheme. And now again, our server can sort of homomorphically decrypt these ciphertexts to translate from one representation to the next. And this is exactly going to let it recover the large sort of sparse LPN encryptions of its encrypted inputs x. So really, again, here we're playing this homomorphic decryption trick to translate from one scheme to the next. And the scheme we're translating to is now our sparse LPN scheme with the huge ciphertexts. And just as an aside, for this orange scheme here, we're actually also going to use an encryption scheme that's based on the hardness of sparse LPN. And really, you can just think of this as sort of masking the input x with a PRG that we get from sparse LPN. Okay, so what do we get when we put this all together? So what's our final construction? Well, again, our construction is going to use these three schemes. So first, this orange scheme, which has cheap decryption. Then this green scheme, which is our sparse LPN scheme that we built with the huge ciphertexts that is homomorphic. And then this pink scheme, which is just linearly homomorphic. And so what our user is going to do is it's first going to sample a secret key from each of these schemes. And then it's going to publish an evaluation key, which is just going to contain the material for performing these translations from one encryption to the next. So really, you should think of this evaluation key as a chain of encryptions of one scheme secret key under the next. So it's a green encryption of the orange secret key, and then a pink encryption of the green secret key. Okay, so that's the evaluation key. And so now, whenever our user wants to upload ciphertext to the server, it can just upload these short ciphertexts using the orange scheme. And now the server locally in its head is going to be able to translate these short orange ciphertexts into these large green sparse LPN ciphertexts that encrypt the same value. Then it's going to use this homomorphism of these big matrices to evaluate its function f. And finally, when it's built the output matrix, it's again going to use the evaluation key to shrink this down to a linearly homomorphic ciphertext that encrypts the same value. So we're sort of going to start with small ciphertexts, we're going to expand, we're going to compute, and then we're going to shrink them back down again. And so really what we have here is that all of the ciphertexts that are actually sent on the wire can be really short and can be compact. And in the paper, actually, we show that they can be rate 1. And all of the blow-up of working with sparse LPN and having to deal with these huge matrices is sort of constrained to the evaluation key and then the computation that happens just in the server's head. Okay, so, so this evaluation key here only needs to be published once, and then it can be reused, and the user can publish as many short ciphertexts as it would like, and our server can evaluate as many functions on the ciphertext as it would like. Okay, so this really is it. Now we just built this entire somewhat homomorphic encryption scheme. And so what I wanted to do now for the last couple minutes is just leave you with some open questions in this area of research. So the first question I wanted to ask is whether we can make these schemes efficient, both in theory and in practice. And I really wanted to point out that the scheme that I showed you here has one sort of major bottleneck to efficiency, which is that the evaluation key is very large because it has to contain one of these huge sparse LPN matrices. And so because of this, the bit length of the evaluation key here is always going to be a polynomial in the bit length of the size of the functions f that our server can evaluate. And so I think a really interesting question in theory is to ask whether we can make this evaluation key here smaller. And then the second thing I wanted to mention is that if we were able to overcome this barrier, so if we were able to shrink this evaluation key, then the scheme seems like it has some appealing properties. So one of them is that almost all of the server's work here is performing these sparse matrix operations, which themselves are a very heavily optimized workload. And the second thing I wanted to mention is that using a variant of Sparse LPN, which was introduced by Dao, Ishai, Jane, and Lin, you can actually work here not only over a modulus that's at least 3, but you can also work over F2. So then the whole scheme works just over bits, which is very fast on modern hardware. The second sort of open question I wanted to ask, sort of continuing in the research direction of this work, is whether we can build homomorphic encryption from either even fewer assumptions or even weaker assumptions. And so what I wanted to do is I wanted to give you just some sort of informal or intuitive justification why it is that these assumptions, so why it is that sparse LPN and linearly homomorphic encryption works and do give us homomorphism. And what I wanted to mention here is that Michencho has this really nice result where he shows that you can boil this Gentry Sahai Waters homomorphism, which is what we used here, down to really 2 properties that are being used. So the first property is that key-dependent message security, which just means you can encrypt sort of functions of the secret key. And then the second property is the ability to homomorphically evaluate your own decryption circuit. And so what Michencho showed is that if you have these 2 properties, you can compose them to sort of apply an operation and then homomorphically decrypt and so on to be able to add and multiply. And also, what we know is that both of these properties are satisfied by lattices. But it turns out they're not sparse LPN. So we argued in the beginning of this talk that sparse LPN does give us this key-dependent message security, which just means that we can encrypt sort of linear functions of the secret. But on its own, sparse LPN can't fully decrypt its own evaluation function because it's not compact. So it can decrypt itself, but the ciphertexts are always going to grow and grow and grow, bigger than the size of the operations that you've performed. And so really here, this part is just rescued in our scheme by adding in a linearly homomorphic encryption. So really, one takeaway or one view of this is that our scheme is sort of decomposing these 2 properties that you need to build homomorphic encryption across multiple assumptions. So instead of having just one assumption like LWE with both properties baked in, we're saying you can spread them out across 2 assumptions. And so I think it's a very interesting question to ask if you can push this further, if you can do similar things with other assumptions, or to build other cryptographic primitives. And finally, maybe the most difficult but also most exciting question here is whether we can get even more from our schemes. Right, so the schemes I showed you today are just somewhat homomorphic, but it would be very cool to get to fully homomorphic encryption. And so what I wanted to do is just end by sketching two sort of high-level approaches and where they seem to hit a dead end. So one approach to getting to fully homomorphic encryption would be to just try and compute more. So right now, we're using these large sparse LPN matrices to perform computations. And really, what's bottlenecking the number of computations that we can perform is the error growth. And so we know that in the lattice world, to control the error growth, you can use bit decomposition to keep all of the values in your ciphertext small. But here in the sparse LPN world, we need to keep the number of errors small. So, and what we're doing here to do that is really we're keeping our ciphertext sparse, but as we compute on them, they get less and less sparse. So really, a very interesting question here is whether there's some analogous gadget to bit decomposition that could sort of sparsify the ciphertext as we compute on them, and then be able to extract more homomorphic operations. Okay, so that's one open question, which would be very cool. It seems maybe hard. And the second possible approach to getting to fully homomorphic encryption would be to bootstrap. So the idea here really is to sort of follow in Gentry's footsteps and to close the loop here. So it would be to find a way to decrypt our linearly homomorphic ciphertext under our somewhat homomorphic scheme. Because if we could do that, then we could publish sort of an encryption of our secret key, and we could always sort of loop around in this scheme, and we could keep computing forever. But really, the challenge here is that we don't know of a linearly homomorphic encryption scheme that has cheap enough decryption. So where the decryption function could be implemented in less than log n multiplications followed by n additions. And so an open question here is whether such a scheme can exist, or on the flip side, whether there are ways to rule it out. Great. OK, so thank you so much. So this talk was about how we can combine this sparse learning parity with noise assumption with a linearly homomorphic encryption scheme to build something much more powerful. And specifically, we've built somewhat homomorphic encryption, where we can compute a few multiplications and then many additions on encrypted data. I think there are really tons of open questions here, and you can find our paper online, and I'm happy to take any questions. Thanks so much.